In this video, we will introduce the second of the five major classes of organic reactions, substitution reactions. We'll explore the two main types, Sn1 and Sn2 reactions, covering their key components, understanding their differences, and identifying the reaction conditions that favor one mechanism over the other. We'll also discuss how to differentiate nucleophilicity from basicity, as well as how to identify good versus poor nucleophiles and assess leaving groupability, distinguishing between good versus poor leaving groups. In a previous video, we explored how the framework of a chemical reaction involves analyzing which bonds are broken and which are formed. We've already seen this concept in action with acid-base reactions, such as Brønsted-Lowry acid-base reactions. Substitution reactions follow a similar pattern, but in these reactions, one bond at a carbon atom breaks while a new bond forms. For example, in the reactions shown below, a carbon-halogen bond is broken and replaced with either a new carbon-halogen or carbon-oxygen bond. In substitution reactions, the two reactive partners are the electron-rich nucleophile and the electron-poor electrophile. The term nucleophile means nucleus-loving, reflecting its tendency to donate a pair of electrons to form a new covalent bond. In other words, it acts as an electron pair donor. You may recognize this definition from our discussion of Lewis bases, as nucleophiles are, in fact, Lewis bases. The second reactive partner, the electrophile, meaning electron-loving, is a species that accepts a pair of electrons to form a new covalent bond. In other words, it acts as an electron pair acceptor. Once again, this aligns with our discussion of Lewis acids, as electrophiles are, in fact, Lewis acids. Substitution reactions resemble Brønsted-Lowry acid-base reactions, except that a bond forms and breaks at a carbon atom instead of a proton. Recall that the four components of a Brønsted-Lowry acid-base reaction are the acid, base, conjugate acid, and conjugate base. In these reactions, the electron-rich base donates electron density to the proton in the acid, generating the corresponding conjugate acid and conjugate base. Substitution reactions follow a similar pattern. The four components are the nucleophile, the substrate or electrophile, the product, and the leaving group. In this case, the nucleophile donates electron density to the electrophilic delta plus carbon atom in the substrate, which is bonded to an electronegative chlorine atom. The chlorine leaves as the leaving group, resulting in a product where the nucleophile takes its place in the starting material. In a substitution reaction, the substrate refers to the molecule that contains both the electrophilic carbon and the leaving group. The electrophilic carbon, known as the alpha carbon, is directly bonded to the leaving group. The beta carbon is the carbon adjacent to the alpha carbon, followed by the gamma carbon, and so on along the chain. The leaving group, as the name suggests, is the group that departs from the substrate, making room for the nucleophile to take its place. By comparing the two types of reactions side by side, we can better understand their similarities. In both cases, the electron-rich oxygen in the hydroxide ion performs a nucleophilic attack on an electron-poor delta plus species on the proton in the acid-base reaction and on the electrophilic carbon in the substitution reaction. In the substitution reaction, this attack causes the carbon-chlorine bond to break as the carbon-oxygen bond forms, releasing chloride ion as the leaving group, analogous to the conjugate base in the acid-base reaction. At this point, many students encounter the same question. Hydroxide is present in both reactions, but in one it acts as a base and in the other as a nucleophile. So what exactly is the difference between nucleophilicity and basicity? Let's take a moment to address this question and also explore what makes a good versus poor nucleophile and leaving group. First, it's important to recognize that while basicity and nucleophilicity are related, they describe different behaviors. All nucleophiles are, by definition, Lewis bases because they donate a non-bonding pair of electrons. However, these terms diverge based on their targets or electrophiles. Basicity refers to donating electrons to an electron-poor proton, while nucleophilicity describes donating electrons to an atom other than hydrogen, typically carbon in organic chemistry. We have seen before that we can measure basicity as an extension of acidity using pKa's, which is a reflection of the position of the equilibrium between an acid and its conjugate base. Moreover, because protons can be more easily transferred, these reactions exist in an equilibrium and are more easily reversible. In contrast, many reactions involving nucleophiles are not easily reversible, so we typically do not use equilibrium arrows for these reactions. Since reactivity cannot be measured through equilibria, it is instead assessed based on reaction rates. For first-row elements, we generally expect the relative nucleophilicities to correlate with the proton affinities, basicity of their conjugate acids. Reaction rates do not always correlate with stability. While nucleophilicity roughly parallels basicity, two additional factors influence nucleophilic reactivity: steric hindrance and solvation. Steric hindrance refers to the difficulty a nucleophile faces when reacting with an electrophile due to spatial crowding around the reactive site. We touched on this concept earlier when discussing the conformations of alkanes. Bulkier groups can make it harder for molecules to approach each other. Reactions where a carbon atom is the electrophile are often more challenging than those where a proton is the electrophile, as the orbitals involved are less accessible. This steric effect slows the reaction and reduces the nucleophile's effectiveness. Solvation refers to the impact of the solvent on the rate of the reaction. Specifically, some solvents can affect the nucleophilicity of a Lewis base through hydrogen bonding interactions. For example, polar protic solvents such as water or alcohols stabilize nucleophiles via hydrogen bonding, decreasing their reactivity. Now that we've differentiated between nucleophilicity and basicity, let's explore the factors that contribute to nucleophilicity and what makes a good versus poor nucleophile. The main factors we'll discuss are charge, electronegativity, solvent, and steric hindrance. Just like with basicity, nucleophilicity increases with greater electron density on an atom. As a result, the conjugate base is always a stronger nucleophile than its corresponding acid. Similarly, across a row of the periodic table, nucleophilicity, like basicity, increases with decreasing electronegativity. Since nucleophilicity involves donating an electron pair, atoms with lower electronegativity are more likely to share their electrons, making them better nucleophiles. An exception to this trend is the halide ions such as iodide, bromide, and chloride, which are excellent nucleophiles despite being rather poor bases. Their low basicity makes them less likely to abstract a proton, but they remain effective at attacking electrophilic carbon atoms in substitution reactions. The next two factors are unique to nucleophiles and not something we've encountered with bases. Unlike basicity, nucleophilicity is not an inherent property of a given species. It can be influenced by reaction conditions, such as the solvent in which the reaction takes place. There are two general types of solvents used in substitution reactions: polar protic and dipolar aprotic solvents. The choice of solvent can have different effects on the nucleophilicity of certain nucleophiles. A polar protic solvent can engage in hydrogen bonding with a nucleophile, forming a shell of solvent molecules around it. This solvation stabilizes the nucleophile and makes it significantly less reactive, as its non-bonding electron pair interacts with the electron-poor hydrogen atoms in the solvent. Examples of commonly used polar protic solvents are water and alcohols. A nucleophile's ability to engage in hydrogen bonding decreases as we move down the periodic table. As we know, fluorine is the strongest hydrogen bond acceptor, while iodine is much weaker due to its larger size and lower electronegativity. This means that in a polar protic solvent, fluoride ions will be heavily solvated, making them less reactive. In contrast, iodide ions experience weaker solvation and are more free to participate in nucleophilic attack. As a result, iodide exhibits greater nucleophilicity than fluoride in polar protic solvents. Thiolates are more nucleophilic than hydroxide or alkoxides in polar protic solvents for the same reason. Sulfur is lower on the periodic table than oxygen, reducing its ability to engage in hydrogen bonding. As a result, oxygen-based nucleophiles are more hindered by solvation, decreasing their nucleophilicity compared to sulfur-based nucleophiles under these conditions. Conversely, dipolar aprotic solvents do not contain electron-poor, delta-plus hydrogens that can participate in hydrogen bonding with nucleophiles to any appreciable extent, giving nucleophiles greater freedom in solution. Under these conditions, nucleophilicity correlates well with basicity, and the trends we observed earlier for nucleophiles in polar protic solvents are flipped. Examples of commonly used dipolar aprotic solvents are dimethyl sulfoxide, DMSO, acetone, N,N-dimethylformamide, DMF, and acetonitrile, MECN. Reactions are typically carried out in polar solvents rather than nonpolar solvents because nucleophiles are generally polar species, making them more soluble in polar solvents. In contrast, nonpolar solvents like hexanes struggle to dissolve these polar nucleophiles effectively. The final factor to consider is steric hindrance. Nucleophilicity decreases as steric hindrance increases. In other words, the bulkier a nucleophile is, the slower its reaction rate, and consequently, the lower its nucleophilicity. Comparing the following alkoxides, methoxide, which is the least bulky, would be the best nucleophile, while tert butoxide, which is the most bulky, would be the poorest nucleophile. We will revisit the utility of bulky bases, particularly tert butoxide, in a later video. Now, let's move on to the factors that determine what makes a good leaving group. The leaving group departs from the substrate in a substitution reaction, becoming a Lewis base as the carbon leaving group bond breaks and transfers electrons to the leaving group. Substitution reactions favor the formation of a stronger nucleophile carbon bond while breaking a weaker carbon leaving group bond, making the reaction energetically favorable. The relative strengths of these bonds generally correlate with the proton affinities, basicities, of the nucleophile and the conjugate acid of the leaving group. Hence, weaker bases make better leaving groups, as they are more stable with the extra electron pair after leaving. A pKa table is a helpful tool for determining leaving group ability. Groups with lower pKa values make much better leaving groups because their conjugate bases are extremely weak bases. An important point to note is that the conjugate acid of a leaving group is always a better leaving group. For example, hydroxide, OH-, and alkoxides, RO-, are strong bases and poor leaving groups. However, converting them into their conjugate acids by adding a strong acid makes them much better leaving groups. The pKa of the conjugate acid of a protonated alcohol is the same as that of hydronium, H3O+, which is around 0. In contrast, the pKa of water, the conjugate acid of hydroxide, is about 14. This difference shows that water is approximately 10 orders of magnitude more favorable as a leaving group than hydroxide at 25 degrees Celsius, highlighting why protonation significantly improves leaving group ability. In contrast, the conjugate base of a leaving group is always a worse leaving group, following the same logic in reverse. Strong bases are poor leaving groups because they are less stable with a negative charge and less willing to leave the substrate. Now that we've explored the components of substitution reactions in detail, let's move on to the two main types of substitution reactions, starting with the Sn2 mechanism. In an Sn2 reaction, the nucleophile attacks the electrophilic carbon in the substrate from the opposite side of the leaving group, displacing the leaving group in a single concerted step. Below is the arrow pushing diagram illustrating the mechanism. The name Sn2 stands for substitution nucleophilic bimolecular, referring to the rate determining step of the reaction. This means that the reaction rate depends on the concentrations of both the nucleophile and the substrate, making it a second-order reaction overall. Experimentally, the reaction rate of Sn2 reactions is fastest for smaller, less sterically hindered substrates. Methyl substrates exhibit the highest reaction rates, while tertiary substrates react the slowest due to increased steric hindrance, which hinders the nucleophile's approach to the electrophilic carbon. The most widely accepted explanation for how an Sn2 reaction proceeds is through what organic chemists call a backside attack. In this mechanism, the nucleophile approaches the electrophilic carbon 180 degrees opposite the bond to the leaving group. As the carbon nucleophile bond forms, the carbon leaving group bond breaks simultaneously. Because the transition state reflects the simultaneous formation of the nucleophile carbon bond and the breaking of the carbon leaving group bond, Sn2 reactions are classified as concerted reactions. This means that the entire process occurs in a single continuous step, with no intermediates. The transition state reflects both the inversion of stereochemistry in the product and the reaction's sensitivity to steric hindrance. As the nucleophile attacks the electrophilic carbon from the opposite side of the leaving group, the stereochemistry inverts, producing a product with the opposite configuration. At the same time, bulky groups around the carbon hinder the nucleophile's approach, slowing the reaction. This explains why less substituted alkyl substrates, such as methyl or primary alkyl groups, react at much higher rates than more substituted ones. The simultaneous involvement of both the nucleophile and the substrate in the rate determining step explains the bimolecular rate law for Sn2 reactions. The reaction rate depends on the concentrations of both the nucleophile and the substrate, making it a second-order reaction overall. The Sn2 reaction is highly versatile because as long as there is a good leaving group, it can be used with a wide range of nucleophiles to synthesize a variety of different functional groups. These reactions are usually carried out in dipolar aprotic solvents, such as dimethyl sulfoxide or acetone, which reduce solvation of the strong nucleophile, giving it greater freedom to attack the substrate. The second main type of substitution reaction is the Sn1 reaction. The Sn1 mechanism differs from the Sn2 mechanism in three key ways. First, unlike Sn2 reactions, which proceed fastest with less substituted carbon substrates, Sn1 reactions are fastest with tertiary substrates and slowest with primary and methyl substrates. Second, as its name suggests, the Sn1 mechanism follows a unimolecular rate law, meaning the reaction rate depends only on the concentration of the substrate, not the nucleophile. Finally, Sn1 reactions are non-stereoselective, producing a mixture of both inversion and retention products. Let's break down this mechanism to better understand these key differences. The most widely accepted explanation for how an Sn1 reaction proceeds is through a stepwise mechanism involving a carbocation intermediate. In the first step, the leaving group departs, generating a carbocation. In the second step, the nucleophile attacks the carbocation to form the product. This mechanism aligns with the experimental observations described above. In the stepwise mechanism, the first step, where the leaving group departs to form a carbocation, is the rate-determining step. The second step, in which the nucleophile attacks the carbocation, occurs rapidly, explaining the unimolecular rate law, which depends only on the concentration of the substrate. The formation of a carbocation intermediate also explains why Sn1 reactions favor tertiary substrates over primary or methyl substrates. More substituted carbons stabilize the carbocation more effectively through inductive effects, making these intermediates form more readily compared to less substituted carbocations. Additionally, because carbocations are planar, the nucleophile can attack from either face of the molecule, resulting in a mixture of inversion and retention products. These reactions are usually carried out in polar protic solvents, such as water or alcohols, which stabilize the leaving group and the transition state via hydrogen bonding, lowering the energy barrier for carbocation formation. Let's wrap up the video with a summary of the key differences between Sn1 and Sn2 reactions. The rate law for Sn1 reactions is unimolecular, depending only on the concentration of the substrate, while the rate law for Sn2 reactions is bimolecular, depending on the concentrations of both the substrate and nucleophile. As a result, Sn1 reactions proceed through a stepwise mechanism with two steps, while Sn2 reactions follow a concerted mechanism, occurring in a single step. The barrier for Sn1 reactions is carbocation stability. Tertiary substrates have lower energy barriers because they stabilize the carbocation better through inductive effects, while primary and methyl substrates are much less favorable. In contrast, the barrier for Sn2 reactions is steric hindrance. The more substituted the substrate, the harder it is for the nucleophile to access the carbon's orbitals. Thus, methyl and primary substrates react faster than tertiary substrates in Sn2 reactions. Since Sn1 reactions depend on the formation of a carbocation, they do not require a strong nucleophile and can proceed with weak or neutral nucleophiles. On the other hand, Sn2 reactions require a strong nucleophile, often carrying a negative charge, because the reaction rate depends on both the nucleophile and the substrate. Sn1 reactions typically occur in polar protic solvents, e.g., water or alcohols, which stabilize the leaving group and the transition state via hydrogen bonding, lowering the energy barrier for carbocation formation. In contrast, SN2 reactions are favored in dipolar aprotic solvents, DMSO or acetone, which reduce solvation of the nucleophile, giving it greater freedom to attack the substrate. Finally, SN1 reactions are non-stereoselective, producing a mixture of inversion and retention products, while SN2 reactions result exclusively in inversion of configuration at the electrophilic carbon. As always, let's do some practice. For each of the pairs of reactions below, circle the reaction that has the greater reaction rate constant. Clearly, explain the basis of your choice in each case, and for the more favorable reaction, draw an arrow pushing mechanism to depict the movement of electron pairs involved in forming the product. Feel free to pause the video and try these problems on your own first. In the first pair of reactions, both substitution reactions are expected to proceed via an SN2 mechanism. Both substrates are primary bromides, and the combination of a good nucleophile and a dipolar aprotic solvent favors the SN2 pathway. The electrophile in the top reaction experiences greater steric hindrance in the SN2 transition state due to 3 beta branching substituents, meaning the electrophilic alpha carbon is bonded to a sterically hindered adjacent beta carbon. As a result, the less sterically hindered primary bromide will react more quickly, giving it a higher rate constant. Since this reaction proceeds via an SN2 mechanism, we can depict the electron movement with the following arrows. The electron-rich carbon of the nitrile group performs a backside attack on the electrophilic carbon bonded to the bromine leaving group. Simultaneously, the electrons from the carbon-bromine bond are transferred to the bromine, allowing it to depart as the leaving group. In the second pair of reactions, both are carried out in a polar protic solvent without a strong nucleophile, favoring substitution by an SN1 mechanism. The substrate in the top reaction will form a more stable tertiary carbocation intermediate, whereas the substrate in the bottom reaction would result in a very unstable primary carbocation. The transition state leading to the more stable carbocation will be lower in energy, making the SN1 pathway more favorable for the top reaction. In contrast, the primary chloride would likely need to react via an SN2 mechanism. However, the transition state energy for this pathway would be relatively high due to the poor nucleophilicity of water as the nucleophile. Since this reaction proceeds via an SN1 mechanism, we can depict the electron movement with the following arrows. In the first step, the electrons from the carbon-chlorine bond are transferred to the chlorine atom as it departs, generating a tertiary carbocation. In the second step, water acts as a nucleophile, attacking the electron-deficient carbocation in a Lewis acid-base reaction to form an oxonium ion intermediate. Finally, another water molecule in solution deprotonates the oxonium ion, yielding the tertiary alcohol product. In the third pair of reactions, both substitution reactions are expected to proceed via an SN2 mechanism. Both substrates are primary chlorides, and although the reactions take place in a polar protic solvent, the SN2 pathway is still favored since SN1 would require the formation of a very unstable primary carbocation. Since the substrates and reaction conditions are the same, the difference in reaction rates will depend on the nucleophiles. For first row elements, nucleophilicity roughly parallels the proton affinity of their conjugate acids. The pKa of the conjugate acid of methoxide, methanol, is approximately 16, which is much higher than the pKa of the conjugate acid of acetate, acetic acid, around 4.76. This makes methoxide a much better nucleophile than acetate, resulting in the bottom reaction having the greater rate constant. Since this reaction proceeds via an SN2 mechanism, we can depict the electron movement with the following arrows. The electron-rich oxygen in methoxide performs a backside attack on the electrophilic carbon bonded to the chlorine leaving group. Simultaneously, the electrons from the carbon-chlorine bond are transferred to the chlorine, allowing it to depart as the leaving group. As always, thank you for watching, and I'll see you next time.